Hi, this is section 3.3. We're still talking about probability. We're going to talk about what I call OR problems. Or, again, just like and at least, the or is a keyword that you'll often see in the problem. So, what's the probability that I'm going to wear the red shirt or the blue shirt? That's kind of how those are going to sound. In order to set this up, we're going to start with a little vocab again. The vocab for this section is the term mutually exclusive. So if two events are mutually exclusive, that means that they can't happen at the same time. So for example, it can't be raining and not raining. Those two things can't happen at the same time. We would call those mutually exclusive. As opposed to owning a cat and owning a dog, I could have both. So, and the way that this comes into play with OR problems is that the formula, if I want you to find the probability of event A or event B, the way that you do that is you add. That's the overarching plan. But there's a caveat, just like with the and problems. The and problems you're going to multiply, but you have to deal with that whole B given A situation. This is going to be similar in that we're going to add these. It's going to be the probability of A plus the probability of B, but you have to subtract off the probability that both happen at the same time. So the way we write that in math is this: A intersect B. Okay, the way I like to say this in English is this is like the overlap. So let me show you it in the table setting. Let's say that we have a table. Whoa, that's not how I wanted to draw that. Let's do this. We've got a table, and let's just say we're going to measure again men and women, and we're going to have cats and dogs. So the number of men and the number of women who own cats and dogs, we're going to go 10, 20, 30, 20, and 50, say. Okay. If I want to know what's the probability that I select one person who is a man or owns a dog. Now, let's just look at this, and I think you'll understand the overlap after you see it in this context. The first question I have is, what's the probability that I'm going to select a man? So these are all the men in my survey. And typically your homework's going to have these totaled up for you, but we'll just do that in our head. So I've got 10 men who own a cat, 30 who own a dog. So there are a total of 40 men in this situation. So I would say this is 40 over, what's our total? Let's see. Let's figure that out real quick. There's 40 here. There's 70 here. So that means I've got a grand total 7, 8, 9, 10, 11 of 110. Okay. There's 110 people in the chart. The probability of a man is how many men over the total. Now let's do dogs. How many people are there that own a dog? Well, that's all of these people right here. So here there's a total of 50 plus 30 is 80 out of 110. And the formula says up here that I'm going to have to add them. Now, what's the problem? The problem in this chart is that you counted some people twice, right? Look at the men and look at all the dog owners. So I've got 30, there's 40 men, but 30 of them own dogs. So I've counted those 30 twice. So this part of the formula that is minus the probability of the overlap, or the probability of A intersect B, is who did you count twice? That's kind of how I explain it conceptually. Who did you count twice? And if you're taking your chart and you're circling like I've been doing, it'll be where your circles overlap, will be this. So I'm going to take a look at this chart, and I've got 30 people right here who are dog owners and also men. So I'm going to subtract off 30 over 110, and that's going to give you your probability. So this is going to be 15, and this is going to be a 90 over 110 is going to be your answer. Reduce it, turn it into decimal, however you want, but that's the procedure for these problems. So in charts, it's easy to figure out the overlap if you just draw your circles, figure out where they overlap. Now, what if I say, well, maybe we need a bigger chart for this. Let's make a chart, and let's add another animal in here. Let's say we've got men and women, but now we're going to have cats and dogs, and what's our other animal? We'll see rabbits. My son wants to get a rabbit. I don't really want rabbit poop all over my house, but you know, we're in conversations. All right, so rabbits, let's say there's 10 men who have a rabbit, and let's say there's 10 women who have a rabbit. So now we've got another category. So let's say, for example, I say, what's the probability that I randomly select one person, and that one person owns a cat or owns a dog? So look at what happens to our chart now. If I circle all the cat owners, I've got 10 men and 20 women. And then I circle all the dog owners, there's 30 and there's 50, 30 men, 50 women. There's no overlap for those things. These are mutually exclusive in this chart. Now, conceptually, they're not. We all understand that you can own a cat and a dog. But according to the chart, there's nobody in this chart that owns both. Okay. Now, I might have a chart that says both, and that would be a different situation. But right now, this chart is only like, these are solely cat owners, solely dog owners, and rabbits. So in the context of this problem, these would be mutually exclusive. There's no overlap. So my probability would be probability of how many cats you have, which is 30 over, where are we at now? 10, 20, 130, plus a dog, which is going to be 80 over 130, minus 0, basically. I don't have to write that, but just to be thorough, because they're mutually exclusive in this setting, there's no overlap and there's no subtraction. So that's why sometimes I'll say really quickly in shorthand, and is multiply or is add. It's actually more than add. You also have to subtract off the overlap, but that's kind of how I delineate the formulas. Now, I also want to talk to you about the English of this. Let's think about, if I say, what's the probability that I select one person from a chart, and you have, you get either a dog owner or a man. That was our example previously. Or I change it to an and problem. The way I write an and problem is, what's the probability that I select two people and I get a dog and a man? Now, I want you to understand a fundamental difference between these two questions. The or question is always going to be one event. I'm selecting one person and I'm giving you options for who you select, this or this. It's still one event, so there's one total probability. In an and problem, you're doing multiple events. So if I'm dealing cards and we're talking about the hand that you got in the cards, I know that's an and problem because there's multiple events. I'm going to be dealt 5 cards. But if only one person's being selected, then it's an or problem. So it's another way to decide if it's an and or an or, because we've talked about before, like sometimes I don't actually use the word and. Like I could say, what's the probability that I get dealt 2 queens? Another way to identify that as an and problem is I'm getting 2 things given to me. That makes it an and problem, as opposed to what's the probability that I get a queen or a king? That's actually one card with multiple options. So if that's helpful in deciding what type of problem, because on your exam, these will all be mixed together. So I wanted to give you that tool if that's helpful. Some of your problems also on, well, let's do a card problem. Let's pull down our set of cards here again that we've used in the past. I've got a set of cards here. I've got 1s through 6s, and each of those cards has either a fish, a cat, a bird, or a dog on it. So I've got 4 of each number, and here we are. So let's say, what's the probability that I get a dog or a 3? So let's go one at a time. Don't try to attack this all at once. Don't try to just write down the answer or go a piece at a time. It's always first thing first. How many dogs are there? So I've got 6 dogs out of, what did we decide? We've got 24 cards. Okay. Now, how many 3s are there? There's 4 of those. Let me circle them for you. So I've got 4 3s, and I've got 6 dogs. So I've got 6 over 24 plus 4 over 24. Now the question is, did you count anybody twice? The answer is yes. I counted this card right here, which is the dog with 3 on it. I counted that twice. So these are not mutually exclusive events, and I need to subtract off 1 over 24. So 6 plus 4 is 10, minus 1 is 9. My probability is going to be 9 over 24. Now, these OR problems are going to typically give you higher probabilities because you've got options. So if I don't have to get dealt a queen, if I could get dealt a queen or a king or a jack, then I have a higher chance of getting that because there's more options. So these will tend to have higher probabilities than AND problems. The at least problems will be smaller probabilities, typically. The other way that you will encounter these OR problems is they will just already build, just like with the ANDs, they'll already build the fractions for you. So they'll say like 23% of the population owns a truck, 30% of the population owns a cat, and 15% of the population owns both. So what they're doing here is you don't have to build the fractions. They're already built for you and put in percentage form, and they are telling you the pieces and the overlap in this situation. So if I ask you, what's the probability of selecting a truck owner or a cat owner, you're going to do the same formula, but you don't have to build the fraction. We're going to take a truck owner, which is 23%, so I'm taking 0.23. I'm going to add that to the cat owners, which is 0.30, and then I'm going to subtract off the people I counted twice, which is the ones that have both, where they overlap. So I'm subtracting over 0.15. Calculate that out, and that is your probability. That's all for this section. Hope this is helpful, and next time we will talk about combinations and permutations. See you soon.